Okay, so I'm here to talk about Apache Drill, which is a project that we've kicked off MapR, the company I work for, but it's not a MapR project. It's right now it's in the Apache Incubator. So I want to talk about sort of the motivations behind it, and then our plans for what we actually want to do. So first, a little bit about me. I went to school. I worked on distributed databases, distributed file systems, and now I'm working on Drill. And just for context, MapR is a company that is in the Hadoop space. I'm sure a lot of you guys are familiar, but in case you're not, the basic idea is that, like several other companies, Cloudera, Hortonworks, we deliver a Hadoop distribution. The differentiator for us is that we have our own file system. It implements HDFS. That gives us a bit more flexibility to do a bunch of things. We can implement NFS real nicely. It gives us some performance benefits. But overall, you can just think of us for this conversation as MapR is excited about distributed databases, distributed file systems. So we have a lot of customers who run MapReduce jobs. And this is great. We're not trying to take that away. But a lot of times they'll say, okay, we have all this data that's loaded into your cluster, right? You have a several hundred node cluster, and you want to actually look at the data. Well, a lot of times you can run a nice long batch process, and that works really well. But what happens when you want to look at data over that's very recent? Well, sometimes that fits in HBase, but if you're trying to run a more complicated workflow, there's not really a great solution. So at Google, they run into the same issues, it seems like, before everyone else, or they at least talk about them before everyone else. And so they notice this. There's a lot of different problems that they're trying to address in this real-time space. Event detection. How do we monitor all the sensors in some warehouse and try to detect anomalous events? Well, you'd like to know within a couple minutes, not within, okay, I'm running a batch process at the end of every day. So if you sort of look at the systems that are out there for doing these sort of data processing tasks, on one side you have MapReduce, batch processing, and you're generally not running jobs that take less than a minute. Maybe you can run a 30-second job, but for the most part you're running jobs that are in this minutes to hours to even multiple days category. And you're processing a lot of data. And you have this data model MapReduce, which most people here know and hopefully love parts of. And that's great. MapReduce exists. There's Hadoop MapReduce you can use. If you work at Google, you can use theirs. Other people have developed different MapReduce-like things, but MapReduce is the general solution for that space of batch processing. On the right side, we have tasks like stream processing. So you're having some sort of feed of data coming in, and you want event-driven processing. Every time a new thing shows up on your Twitter feed, how do I update your, how do I show you a new ad? I don't know if this is what Twitter wants to do, but let's just take a Twitter feed as an example of a stream. You can analyze events on it. So there have actually been a couple different projects that have shown up recently in the stream processing space. Storm is one that's actually at Twitter now, or at least now it is. S4, which I'm not too familiar with, but it's an Apache project. So besides these two categories, batch processing and stream processing, we now have this interactive processing. How can I run queries that can return in hopefully less than a second? Maybe they can run for several minutes, but ideally I want queries that are fast enough that they can be viewed as interactive. If I put a GUI that's going to run one of these queries on top of it, if it pauses for a minute, that's a pretty bad user experience. And ideally, I'd like to be able to run actual queries and not develop a job application that then writes key-value pairs. I'd like to say, SQL, it's pretty close to good. It does a good enough job. There's not really a good tool for that. So at Google, they came up with this project, and they called it Dremel. Well, at least internally they call it Dremel. And Apache Drill is sort of aiming to do that same, aiming for that same sort of column. So I'm going to get a little background on Google before talking about what we want to do, and there's some differences. So Google released this paper back in 2010, and it's used all over the place at Google now. So if you talk to people about Google, they're like, yeah, we use this thing, and it's great. A lot of statistics, various things are shoved through Dremel for fast scoring. And if you look at the paper, they actually have some pretty impressive statistics about how much data they're processing, both in terms of overall volume and just also the number of records that they're processing per day. It's very, very large. So it's not like, we're reinventing MySQL. It's a totally different tool. Another thing that's interesting about this is that they didn't use the same sort of data model that people are used to if they're in the relational database world. In a relational database, you can nest columns, but it's a very painful thing. It's not really well supported by most databases. Whereas, as people have realized with MongoDB and JSON and Protobufs, which is I think a lot of inspiration for Google, although I don't work there. But with Protobufs is that it's great to be able to nest data. A lot of times that is a much better model than trying to flatten everything out. So it's a combination of this nice data model together with a SQL-like language, and the goal is to make it fast. So you can actually see Dremel now by going to Google's website, and they have this thing that's called BigQuery that is their public API for Dremel. So I'm actually not too familiar with the internal tools that Google uses to interface with Dremel. But as an external user, you can go and run queries that use the same Dremel processing engine that they talk about in the paper. So you can see a little bit of an example here. I don't want to go too much into depth about this particular query, but the idea being that, Dremel is available for you now, but you have to import your data to Google's website, and you have to run it as this hosted service. So that works fine for some people, but if you have a lot of data, if you don't really want to upload your data to Google, which fits for a lot of companies, then BigQuery is not quite the answer for you. But you can go and play around with it, and it seems to be a nice service. So the idea of Apache Drill is how can we take the same sort of service and make it an open source, fully runnable project. You can deploy it wherever you want. You don't have to, upload your data anywhere. If you have a data center, you should just be able to process your data in place. So here's sort of a big picture of how most databases work. And I'll dive into some of the details. So you start out, you have some place that receives all your queries. Calling that the driver, some people call that some wrapper around the socket. Not really interesting. So you get some sort of query. And SQL, all the queries are declarative, and they all come across as text, right? It's just a pure string of text that's a SQL query. So that's fed into a parser, and what the parser does is similar to any sort of parser. It produces an abstract syntax tree, which for us, all we're trying to do is make sure, is this a valid SQL query, is it shaped in the right way? Maybe do some, things about, here's where you can put a where clause, here's where what things you can refer to in the where clause. But for the most part, parsing is also pretty straightforward. You take that, and then you want to actually turn that into something that can be executed on your cluster. So this is called the compiler, the optimizer, the planner. It's beautiful words. And these have varying amounts of complexity. If you look at SQLite, for example, you see a much different level of complexity than if you look at SQL Server. But the goal for both of them is the same, which is to take abstract syntax tree, turn it into an execution plan. The execution plan, we want to have sort of a text-driven, way to directly enter the execution plan. I'll go into that in a little bit. But the idea there is that you have this distributed query, it's running, and hopefully it talks to storage. It's not doing abstract computation, it's actually processing the data that you have. So, there's a number of different things that execution engine needs to know. It needs to know, a lot of attributes about your cluster, where your data is. And for us, we'd like to be able to support quite a bit of flexibility. So whereas at Google, they data in protobuf form or in column IO form. For a lot of people, that tends to be not what they have. So we'd like to say, okay, depending on what type of storage you have, you can write your own sort of interfaces to query your data. It's up to you. And then maybe you're not really a big fan of SQL. A lot of people seem to like MongoDB. It has a totally different language. So we'd like to be able to make it so if someone really prefers using that language, they shouldn't be bound by the decisions that we make in our parser. They should be able to write their own parser. So here's sort of a view of using that, having different modalities. So we're calling this query language Drill query language, or DrQL. But let's say it's just a pure knockoff of the BigQuery language. Here's an example where we have some client issuing these SQLite queries. We have another client that's using, cascading or pig. And both of them are going to a common intermediate format, compile down, they can be executed. So, as far as execution goes, is that you have this pre-built query model. It can be extended in different ways, but there's a lot of common operations that people do. So, the ones that are pointed out in the Dremel paper are just aggregations. Essentially, how can you do distributed aggregates? So, there's sort of two layers to think about here. One is that you have a bunch of different operators. So, you can have an aggregate operator, and maybe it's doing local aggregation. It's just doing aggregation on that node. You have scanner operators, maybe it's just operating on a chunk of your table. So if you're running on HDFS, your file is broken down into a whole bunch of chunks. You can essentially think of there being an independent scan operator for each chunk of your file. At another level, you can think of what is the amount of work done on a certain node. And at that point, the differentiation between one operator running on that node and another operator running on that node sort of goes away. So there's different problems to worry about. One problem is how to use serialization. That has to happen at this upper layer of individual operators. Another problem is how do you actually do scheduling? How do you make sure that the global aggregation task doesn't complete until all its child inputs on different nodes finish? So those are sort of the two different layers to think about. So I'm just going to sort of walk you through some of the sort of data flow paths that can be taken, and sort of contrast those to the Dremel. So, you can have all your data stored on a Hadoop cluster, right? There's this HDFS protocol. At MapR, obviously, we're a fan of this HDFS protocol since our file system does it. But even if you're running Apache Hadoop, you still have the same protocol. So let's say your data is all in a Hadoop cluster. You can have different types of format. Maybe you have a format where it's just one protocol buffer after another. It's a sort of row-wise format. Another format is maybe you have come up with some sort of efficient packing scheme to say, well, I can compress data from the same columns together. So if you look at the Dremel paper, they actually spend most of the paper talking about efficient encoding schemes, not actual distributed execution. So we have these two different sort of input types. We have row-based input types, we have column-based input types. And then you can also have your processing also be column-based or row-based. So I think actually the Dremel, I think some of the Dremel paper might actually be row-based processing, but traditional OLTP databases tend to be strictly row-based processing. So SQL Server, I think until 2012, was all row-based processing. Certainly MySQL or PostgreSQL. And then if you compare a lot of the OLAP databases that have come up, Vertica, for example, they tend to be column-based processing. So we like to support both sort of modalities. And then, like I said earlier, have different query languages to form them off from. So, I mentioned DrQL a little before, and the idea is just how close can we get to SQL that also supports nested data in a comfortable way. I don't know if you look at Postgres and try to use arrays, it's not quite as elegant as say MongoDB. I guess that's an example, but so we'd like to be able to support these nested data types. We have a goal to sort of make things compatible with BigQuery. I think we'll probably end up being, if we have a choice between being closer to compatibility with SQL or closer to compatibility with BigQuery, I think we'll probably err on the side of SQL. I guess this is what more flexibility for external tools. And then the idea is that you want to be able to have the query specified enough so that when you're actually processing your data, if you're doing column-based processing, you like to avoid reading as many columns as possible. You need to have your query language expose enough of those semantics that you can efficiently do it. So here's an example of two different data models that support nesting. So on one side we have JSON. This is actually not a nested example, but well, there's JSON. And then, so we like to be able to support a bunch of different other formats. I mentioned protocol buffers before, but even just CSV, TSV, there's some interesting differences between whether or not you know the schema beforehand, in which case it's a lot easier to compress the data in a columnar format if you're aware of the schema. But in something like JSON, there's no schema declared up front. Maybe there's a common schema that tends to be used, but the user may never specify what that is, and you have to figure that out along the way. So being able to handle both those types, JSON or protocol buffers, schema, list versus schema, we want to be able to do both. Here's an example. I think this might have come from the BigQuery documentation. But the idea here is we're doing an aggregation within this nested field name. So going into the exact semantics is not too exciting for now, but it's generally SQL-like. So looking at just sort of the basic things that we're trying to support out of the gate is what does it take in order to do aggregations? So obviously, a select clause, you need to declare what you're actually trying to read. You need a way of specifying where to get it. You want to filter it. You want to aggregate it, and then maybe you want to do some sort of post filter. That summarizes those first 5 clauses. There's a bunch of other clauses in SQL, and we can look at supporting them as time goes on. Join is one example of, yeah, it'd be great to support joins, but there's a lot of common problems. So if you look at BigQuery, they do small joins. I think the restrictions, at some point I think it was 8 megabytes, maybe they bumped that up. I think for BigQuery the idea was that you can do joins against small tables by just shipping around those tables to every single node. For us, we like to ideally support bigger joins, but not a focus right in front. So sort of these operations match down to just a few operators, scan, filter, and aggregate. So you can have different ways of doing each of those operators. Obviously, you need a different scan if you're scanning a columnar sort of format versus scanning a row-based format. You need a different type of filter if you're expecting JSON data versus packed row-bus. But from a logical point of view, there's just 3 real operators to support those first 5 blocks. So just a little bit more about this extensibility to recap. Nested query languages. I don't know if we initially want to try to support the long query language. I'm sure it has a bunch of odd semantics that we don't necessarily need to take on up front, but we want the flexibility there so that the parser is not directly tied into the compiler. We want a common distributed execution engine, so I don't think we need to make that pluggable. The model I was looking at for the sort of the lower layer of how do you do scheduling, how do you do task dependencies, is pretty close to what Microsoft did for Dryad. So you can read the Dryad paper; it's very nice and exciting. And then on top of that layer, there's on top of this sort of Dryad model, there's a per operator. Here's a hash aggregate operator. We want to support a whole bunch of different data formats out the gate, and then we also want to support not just HDFS, but right now, if you want to query your data, it's an HBase. Writing your own filter is kind of a painful thing to do. So ideally, ideally, we'd like to be able to say, okay, your data is an HBase. Well, you can query it with this nice abstract query language. But if someone wants to write a backend to talk, specifically to React, for example, I don't think there should be anything gating in our architecture that prevents you from using React or Cassandra or really any NFS or Google Cloud, for example. So just dive a little deeper on that, how we actually scan data. So when we support join, we actually like to be able to support collating multiple data sets at the same time. How do you sort of combine them? But ignoring that for now, how do you efficiently support scan? So with columnar databases, you have an example where you have, let's say you have 10 predefined columns, and you'd like to scan them. If you only want to look at 3 of those columns, you'd like to do your scans as efficiently as possible, which means you only really want to read data from those 3 columns. So it requires you to push down what fields you actually want to read, and ideally you also like to be able to push the predicates down so they can be evaluated as part of your scan. So a scanner operator needs enough functionality to be able to, or enough smarts from the optimizer to push these pieces down. And then we'd like to also make the scan operators able to have a lot of interesting side effects. So there's been a bunch of database research recently into how do you adaptively convert your data into a format that's efficient for querying. And so the best way to do that is to look at your query load and sort of slowly change it over time. You can look more at database tracking. There's adaptive indexing is another word for this. But all this functionality we're trying to encapsulate in this, underneath this scan API. So, right now we're gathering people for the project. We have a lot of people taking on different components. But just sort of the high-level goals is that we want the core of the project, this execution engine. We're writing in C++. Some of the scanners we want to write in C++, but if you want to interface directly with HTML, well, at some point you're going to Java. So we're trying to give enough flexibility so that people can write backends that don't necessarily require C++. It actually is looking like the optimizer is coming out in Java. That's fine. But basically, we want to make it easy to run. We want to make it be able to run in all customers' use cases. In your data center, you should decide what type of formats you're using. And we want to make it so that it's fault tolerant and all the normal exciting things from distributed systems. So, looking at it from MapR's point of view, right? We're not shipping Cassandra or React, at least not yet. So, we'd like to be able to integrate with the things that people already use on top of MapR. So, HDFS is one thing I mentioned earlier. We actually have our own internal sort of protocol. So, if we can directly talk to that, that's good for us. But that's not a restriction. HBase, mentioned that earlier. HBase actually gives you locality for your data just like HDFS does. You can say, tell me what regions you have, tell me the servers they're on, and you can process the data on those servers. There's some existing data formats. RC files one. I saw another one called Trevny, which is another columnar format. But it's a bunch of different existing Apache projects that we'd like to be able to integrate with. HCatalog is actually another good example of an integration point, is that once you have all your data, you describe all your data, well, if you already shoved all that metadata information into HCatalog, we shouldn't force you to redefine it. So just sort of a high-level goal of, let the user do what they want to do. They're using HCatalog is the thing we'll try to use. So, I think this URL is right. But, so join on the mailing list, come find me at the end of this. If you want to